So you've got a source and you've got a sink. What does this even mean? It means that this describes a source of strength at positive m at z equals 1 and a sink of strength at minus m at z minus 1, which equals minus 1. So we want to find the fluid velocity. So, this isn't exactly the right example, but something like a tap and a drain hole. So you have a source where water is flowing and you have an exit, a sink, where it's going away. But this is a bit more about the particular, instead of just like a generalized water flow. We're looking at essentially a certain point of it. So we're first going to use the general formula, which is something that you're going to have to remember. And what you do is you then substitute in these values. So it's going to be W equals m over 2 pi ln, and then we get z minus 1 minus m over 2 pi ln z plus 1. And we're going to do the fluid. Let's do the fluid at x0. So let's first do the first step. Let's differentiate this. So dw dz is m over 2 pi, and then this differentiated is going to be 1 over x minus 1 minus x plus 1, and we then want to multiply this across and simplify it. So that's then going to become m over 2 pi 1 over x minus 1, and we're going to multiply x plus 1, x plus 1. I'll do a bigger brackets here, minus 1 over x plus 1 and x minus 1, x minus 1. So if we now clean this all up, you're going to then get m over 2 pi x plus 1 over x squared minus 1 minus x minus 1 x squared minus 1, which is very convenient because x minus x is going to disappear. The denominators are exactly the same. So you can have 1 minus minus 1, which is 2. So you're going to get m over 2 pi 2 x squared minus 1. So the 2's are now going to disappear, and you're going to get the solution, which is dw dz, which is m over pi x squared minus 1. So this is in another video that I did where we talk about differentiating a position vector into a velocity, and then you can differentiate it into the acceleration. And it's the same thing that we're doing here. We're differentiating, so we know that dw dz is actually equal to the velocity in terms of x. So that means this here is going to tell us what the fluid velocity of this complex potential function is. And this solution is for the complex velocity, but since we're evaluating along the x-axis, y equals 0. So the flow is purely real and horizontal, and this expression gives the magnitude and direction of the velocity in the x direction. So anyway, you ever turn on your tap or sink, you know what's going on.